Okay, this one is a more numerical proof, and I'm not. In this one, I'm not going to show you what a trace is, but I'm going to do a hand waving proof. So it's actually pretty complicated, but I wanted you to get kind of an idea how you can do something with this a little bit different. So it starts off with the definition of trace, which I haven't talked about in class, but the trace is just the sum of the diagonal elements of a matrix. So it's only defined for a square matrix, and in the case of 1, 2, 3, 4, it would just be 1 plus 4. I just add up the diagonal elements together. There's a theorem that says the trace of any matrix turns out to be the sum of the eigenvalues. And so I wanted to see why this was true. So I started out with just the 2 by 2 case. The trace is a11 plus a12. And I went to the characteristic polynomial, and I wrote it out. And I noticed that in the characteristic polynomial itself, it turned out that the trace was right there. And that's in this quadratic polynomial, that's the negative b, right? Ax squared plus bx plus c. So it's going to be inside your quadratic formula. So it seems to me that when you actually set this equal to 0, the trace will appear, and you'll see that it's the sum of the eigenvalues. I didn't carry that forward. I just wanted to see what it looked like for a 2 by 2 matrix. So I could start there, because if you talk about an n by n matrix and talk about the eigenvalues of an n by n matrix, you're talking about something huge. You know, it could have n different eigenvalues. They could be complex in value. So I wanted to see something I can get my hands on and get a feel for it. So this is an example where starting off with a 2 by 2 is a good idea. Then I thought I'd go to the 3 by 3, and it started getting scary. But I did one of these things. I said, okay, wait a minute. In the example I showed you before, the trace appeared on the second term, right there. So I wonder if the trace appears again on the second term. And in fact, that would be all your lambda squared terms. So I didn't go through and multiply these out. I just looked at where my lambda squared terms are going to come from, and I just isolated them. And I noticed that I got trace here again. It turns out to be trace again. And you can do that too. You can expand it out full on if you want to, but I was a little lazy and I went through and said, like for example, if I do this multiplication here, that's going to give me some lambda cubed terms.
So like after you do like 1 or 2 examples, you can just automatically make the conclusion that for all of the second terms, the trace is going to be there?
Kind of. If you go back and look at the previous thing, the sign was off. It was minus trace here, and it was plus trace here.
So would you do like a one more?
What's your guess that the next one will be? It's probably going to be minus and plus. And so it does turn out, like that was my guess, that this number, if I look back at the first one, it was also swapping signs. It used to be, on the first one it was a positive, then it was a negative. So these are all swapping signs, and if you had E for Calc 2, you know that what you have to do to get something to alternate in signs, you multiply by a -1 to the n. So I don't really care about all the other stuff. I just noticed that the trace was appearing here. And to prove that, you probably need to use mathematical induction. So I'm going to show you math induction proof today, but on something much easier. This one's messy. I can see it's messy because it involves taking a n by n matrix and then breaking down the minors and looking where I'm going to get my lambda to the n-1 terms from, which was okay to do for the cube, but it might be really scary to do like for a fifth one. So I'm not going to prove this, but you can prove it. It's what I call a messy proof. There's some people who go into math, they just love messy things. And the people who work with lots of like fluid flows and computations, and more power to them. I like things that look very clean and pretty. But you can prove if you had messy time. So that U is you. Here's the proof of why the trace is going to be the sum of the eigenvalues. There's a theorem that tells you that if you know the roots, you can take that polynomial and factor out into the roots. You already have used this theorem for easy things in Algebra 2 in high school. You've been factoring things. But you could have square root of 2 be your root, for example. You can still do this factoring. And if you played around with enough math, you know that you can do that. You can write like x plus square root of 2, x minus square root of 2. It just looks messier. And you can also do it with complex numbers. This is a theorem called the fundamental theorem of algebra. Remember the fundamental theorem of calculus? Those are like the big theorems. So the fundamental theorem of calculus is the f of b minus f of a is equal to the integral of a to the b. So that's the big one for calculus. For algebra, it's all about roots. You spent all your time in algebra talking about roots, finding roots, factoring so you can find roots, quadratic formula so you can find roots, drawing pictures on a graph so you can find the roots. It's always about finding roots. So that's why the fundamental theorem of algebra says is if you know the roots, you can factor the polynomial this way. It might not be pretty. Nobody says it's pretty, but you can always do it like this. Well, it turns out if you expand this and gather together the coefficients of the lambda n minus 1 term, this is what you got. Lambda to the n is going to come right, you're going to just multiply through and get lambda to the m. And then you get this term here. It's going to swap in sign on every odd numbered turn of degrees. And so you get this gathering together of coefficients. And that's exactly the eigenvalues, and that's a sum of the eigenvalues. The only way two polynomials can be equal is if their coefficients are equal. And so there you have it. You equate the coefficients of lambda to the n minus 1, and you get the trace of a is exactly equal to lambda 1 to add it up to lambda n. So that was a hand-waving proof because I've left out detail. It's not very clear. I've skipped some things, and I asked you to trust me. And I gave some things for you to do. That's if you really, really want to harass your students, you leave them homework in between the gaps of your proofs. I'm going to skip this part, but it's your homework. In case any of you are thinking of getting your PhD, that's what math professors do.